And we're back with part 3 of chapter 10, energy. So last time we were taking a look at examples of kinetic energy, conservation of energy problems. So now we have another one, speed of a spring-launched ball. So a spring-loaded toy gun is used to launch a 10-gram plastic ball. The spring, which has a spring constant of 10 newtons per meter, is compressed, or sorry, a 10-gram ball, that's important too, is compressed by 10 centimeters as the ball is pushed into the barrel. When the trigger is pulled, the spring is released and shoots the ball back out. What is the ball's speed as it leaves the barrel? Okay, so I have speed coming out. I have spring inside the gun. That sounds like a conservation of energy between spring potential energy. So that would be U sub S going to, and that would be at the beginning, going to at the end, kinetic energy at the end. Okay, so let me set those two equal to each other. And it gives me a spring constant, so that's nice and easy. So I'm going to say that is 1/2 kx squared equals kinetic energy 1/2 mv squared, and I'm solving for the speed. So I'm solving for that v at the end. 1/2 kx squared, k is 10 newtons per meter. So I've got 1/2 times 10 newtons per meter times the change of distance, which is 10 centimeters. Is that right? Compressed by 10 centimeters. That is right. So that's 0.10 meters squared equals 1/2 times the mass of the ball, which was 10 grams, 0.010 kilograms, because there's 1,000 grams in a kilogram, times the velocity squared. Okay, so now it's just a little bit of math. I can get rid of my 1/2 because those will cancel. So 10 times 0.1 is 1 on that side, divided by 0.01 is 100, and then take the square root of it to find v, and v has to equal 10 meters per second. Nice. So the speed as it leaves the barrel should be 10 meters per second. How interesting that all of those values ended up as 10. 10 newtons per meter, 10 centimeters, 10 grams, 10 meters per second. Kind of cool. All right. Next up, where will the sleds stop? Another conservation of energy, but this time with thermal energy. So a sledder starting from rest slides down a 10-meter hill, high hill. At the bottom is a long horizontal patch of rough snow. The hill is nearly frictionless, but the coefficient of friction between the sled and the rough snow, oh, how convenient that the hill is frictionless, but the rough patch is not. Is 0.3. How far will the sled slide along the rough patch? Okay, so this one is potential energy at the beginning. Sorry, I keep using my old conceptual ones. Potential energy due to gravity at the beginning, turning into thermal energy at the end due to friction. So that is going to be the mass times the acceleration due to gravity times the change of distance is going to equal the thermal energy, which would be the force of kinetic friction times the distance that it travels. And I need to know how far will the sled slide. So I'm solving for the change of distance. And I don't have the force of kinetic friction, but I do have that, the coefficient of friction, a sledder starting from rest. Okay, so I know that the force of kinetic friction, I'm going to have to do some more additional playing here because I don't have a mass of the sledder. So that's equal to the normal force times the coefficient of kinetic friction times the change of x. And then the normal force is equal to the weight of the slitter. So that's equal to mg times mu sub k times the change of x. Okay, so now I've got these two things on either side of each other. This is kind of convenient because I'm going to get to cancel some stuff. So the mass is on both sides of the equation. That can cancel. The acceleration due to gravity is on both sides of the equation. That can cancel. The change of y and the change of x are not on either side, so I'm left with change of y, 10-meter high hill, equals the mu sub k, 0.30, times the change of x. Divide both sides by 0.3. 10 divided by 0.3 gives me 33 and a third. So delta x equals 33 meters. Very good. All right, that was kind of fun. Let's keep going. It's a nice little stop and think. Oh, it looks really similar. Person sliding down various hills. But this one is a water park. Look at that, we've mixed it up. It's no longer ice, now it's liquid water that we're sliding down. So Katie slides down each of the frictionless slides shown. At the top, she's given a push, so she has the same initial speed. At the bottom of which slide is she moving the fastest? Okay, so I know that she has some kinetic energy at the beginning, and then she has a change of potential energy, gravitational potential energy, and I'm trying to figure out how much she has at the end. So it looks like each of these slides has the same height, and they do. So she has the same change of gravitational potential energy. So that will translate to the same change of kinetic energy as well. So that means if she starts with the same speed, she will end with the same speed as well. So that would be d. Her speed will be the same at the bottom of all three slides. All right. Let's talk a little bit more and talk about collisions. So collisions is another topic that will make more sense after we get into some other components, specifically momentum. So we'll go more into momentum, but there are two types of collisions. The first type of collision is called an inelastic collision. In an inelastic collision, objects deform and stick together. So if I take a ball of clay and I throw it and it splats on something and sticks to it, that's inelastic. In that case, a lot of the energy is transformed to thermal energy because a lot of the energy is going to deforming the object. My clay goes from this to that. And so there's a lot of it's a scientific term for it. And as a result of all that, you're losing a lot of heat, right? So there's a lot of thermal energy. 96% maybe of your energy is lost to heat. In an elastic collision is what I'm going to call a full bounce. So the objects come together and they fully bounce off each other. There is the same amount of momentum before as after. Well, that's true for an inelastic collision too. But it's a full bounce with no energy lost to heat. So if no energy is lost to heat, then we say all mechanical energy is conserved. All kinetic energy mostly would be conserved. Okay, so our equation for conservation of energy, conservation of kinetic energy in an elastic collision. And this equation would be just for an elastic collision because momentum is conserved in all collisions, but energy is only conserved in an elastic collision. Okay, so I've color-coded everything. This side, my red side, is my before the collision side. This side is my after the collision side. And then I've color-coded green is object 1 and object 1. It continues to exist before and after the collision. And yellow is object 2, which continues to exist before and after the collision. So it's 1/2 mv squared plus 1/2 mv squared equals 1/2 mv squared plus 1/2 mv squared. But then I've labeled mass 1 initial, mass 2 initial, mass 1 final, mass 2 final. And the velocities, same deal. So I can use those equations, set them equal to each other, and see how the kinetic energy is conserved. I can also put those equations together in a perfectly inelastic collision with object 2 initially at rest. If object 2 is sitting still and object 1 runs into it, then I can find their final velocities for object 1 and object 2 using this nice little set of equations here. And it's derived with a bunch of math that's pretty basic algebra, but a lot of steps. Okay. So that looks good. Let's do one more sample problem. Protecting your head. A bike helmet is basically a shell of hard crushable foam, is tested by being strapped onto a 5 kilogram head form and dropped from a height of 2 meters onto a hard anvil. What force is encountered by the head form if the impact crushes the foam by 3 centimeters? Okay, so this one looks like it is an example of gravitational potential energy turning into work. Because it's asking for a force, and I know that force is in the work equation, right? It's doing work on that helmet by squishing it. So I'm going to set gravitational potential energy at the beginning equal to work at the end. That gives me U sub G initial equals work at the end, final. Really, it doesn't need a final because it's work, right? It's the work done on it, but I'm going to say final anyway because I'm contrary like that. So that would be mg times the height equals the force, times the change of distance. So mass times acceleration due to gravity times the change of height. The mass is 5 kilograms times 9.8 meters per second squared times the change of y is 2.0 meters equals the force, that's what I'm solving for, times the change of distance which occurs in the collision, and that's 3 centimeters times, oh, not 3, but I got to change it to meters, so 0.03 meters. Okay. Solve for force by dividing both sides by 0.03 meters, and that'll give me, let's see, 5 times 9.8 times 2 divided by 0.03. Whoa! 3,267. So I'm going to round that to about 3,300 newtons of force. That's a lot of force. It's equivalent to maybe like a batter hitting a baseball, which actually makes sense, right? Bat hitting ball, helmet hitting ground with a head in it. Both of those sound bad, but at least you're wearing your helmet, and the helmet absorbs most of the crashing, not your head. So that is great. Good choice wearing that helmet, everybody. Way to be responsible. Okay, we're to our last little bit. A small ball with mass m is at rest. It is then struck by a ball with twice the mass moving at speed v sub 0. The situation after the collision is shown in the figure. Is this possible? So big mass comes in, hits little mass, after big mass is standing still and little mass is still going. Okay. So we got to figure out if momentum is going to be conserved or if energy is going to be conserved, or either. So in this case, the momentum, 2 mass times velocity, was here, 2 mv, okay? This one is 2 vm. So momentum is conserved, so that one's out. Momentum is conserved. Now, is energy, and that one's out too because momentum is conserved in this case, is energy conserved. Energy originally would be, remember kinetic energy is 1/2 mv squared. I can kind of ignore the 1/2 because it's a constant. So that would be 2m v squared. And then on the other side, it would be m times 2v squared. 2 squared gives me 4mv squared. So I went from 2mv squared to 4mv squared. That doesn't seem very logical. Somehow I've managed to double my amount of energy. That's not possible. Okay, I can't create energy out of nowhere. So I'm going to say the answer is C. No, it's not possible because the energy is not conserved. I have an addition of magic energy. Okay, one last concept, and it is power. Power is the change of energy over the change of time. So how much energy are you putting out in how much time? More power means you're doing stuff real quick. So for example, if I walk a mile versus sprint a mile, both cases I've done the same work. I've moved my body a mile. However, in one, I'm putting out way more power because if I'm sprinting, then I'm doing it in less time. And so I must be having more exertion, more power exertion. And so that might give me a better workout, right? It would do more for my muscles to be sprinting a mile than it would be casually walking a mile. So power is the change of energy over the change in time. Power is also equal to the work over time because work is a change of energy. Or I could solve work for force times distance. And then distance over time gives me velocity. So I could also say that power is equal to force times velocity. It's a different iteration of that equation. This is the one that's on your physics, AP physics sheet. So that's the one that we'll primarily be using. All right, 2 more practice problems. Whoops, 1 more practice problem and a stop and think. Power to pass a truck. Your 1,500 kilogram car is behind a truck traveling at 60 miles an hour, 27 meters per second. To pass the truck, you speed up to 75 miles an hour, 34 meters per second, in 6 seconds. What engine power is required to do this? Okay, so that's a change of kinetic energy. It's movement energy, because I know I've got velocities given to me. So it is power is equal to the change of energy over time. And in this case, it's the kinetic energy over time, and it's the change of kinetic energy, which is going to be equal to the kinetic energy final minus the kinetic energy initial all over time. I don't know why that one got capitalized, which is equal to 1/2 mv final squared minus 1/2 mv initial squared over time. Whew. And I think I can now plug in some values. So that gives me 1/2 times, I'm actually going to pull the 1/2 m out. So it's 1/2 times 1,500 kilograms times v squared, so 34 meters per second squared. Minus 27 meters per second squared, all of it over the change of time, which is 6 seconds. Okay. All right, so a little bit of math here. 34 squared minus 27, clear. 34 squared minus 27 squared times 750, which is 1,500 divided by 2. divided by 6 gives me 53375, or 53,000 watts. Okay, so the unit is joules per second, right? That's joules over seconds, and a joule per second is watt. Yes, that's right. Who's on first? Third base. Yeah, it's a watt. It sounds like what, but it's a unit. W-A-T-T. What's the matter with you? Nothing. So I think it's named after a guy named James Watt. Okay. Is that right? I think his first name was James. So there we are. Engine power is 53,000 watts. And I think in the textbook, they convert it to horsepower for you and say it's like 70 something horsepower, plus the normal horsepower to keep your car going at 60 miles an hour, like pushing against the friction of the road and the air resistance and all the other stuff. So you would require that much engine power. There we go. Stop and think. Last one. 4 students run up the stairs in the times shown. Rank in order from largest to smallest their power outputs, PA through PD. Okay, so power outputs is going to be the amount of energy over time. In this case, they're going upstairs, so that's a change of potential energy. So potential energy, let me see. So this is power is equal to the change of energy over the time. And in this case, it's a potential gravitational energy over time, which is the mass times the acceleration due to gravity times their change of vertical distance over the time. Now for all of them, they're on the Earth, so the acceleration due to gravity is going to be the same. So I'm comparing their mass, the change of time, the change of height and the time. All right, so in terms of doing all that, I'm going to multiply to find a ratio, right? I'll multiply the mass and the change of height and divide by the time. Okay, so mass times change of height divided by time is 80 in that case. 80 times 10 divided by 10, 80. In this case, 80 times, looks like they're still going 10 here and 10 there. So 80 times 10 divided by 8 is 100 for that one. And this is like a ratio of power. Since I'm just ranking, it doesn't ask me to give total values. 64 times 10 divided by 8, 64 divided by 8 is 8. 8 times 10 is 80. And then our big kahuna, 80 times 20 divided by 25. That one's a little bit tougher for me to do mentally. 80 times 20 divided by 25 is 64. Because I'm taking so much more time. Even though I'm doing more work, I'm accomplishing more, I'm getting to the top. It's going slower, so there's less power output. So from largest to smallest, B is the largest. So that would be P sub B is my biggest one, is bigger than the next ones are P sub A, which is equal to P sub C, which is bigger than my last one, P sub D. And there we go. That is power, and that is energy. So we are now done with Chapter 10, Energy. Good job, everybody. Let's crank through some practice problems, all multiples of 5. Full disclosure, number 20 on the question and number 15 on the problems have to do with like rotational motion. So if you're less familiar with that, don't worry about it. you will become more familiar with it when we do rotational motion in unit 6 and 7. All right, enjoy working on those, and I will see you next time.